Take a moment to pause and consider something extraordinary. Right now, as you're watching this video, somewhere in the vast expanse of our galaxy, an alien civilization might be doing exactly the same thing, gazing at their own screens, contemplating the very same question that has haunted humanity for centuries. Are we alone in the universe? This thought-provoking possibility isn't just the stuff of science fiction or late-night speculation. In fact, this fundamental question about our cosmic solitude has so deeply intrigued the scientific community that it led to the creation of one of the most fascinating mathematical equations in the history of astronomy. What makes this equation particularly remarkable is that it attempts to quantify something that seems beyond our reach: the number of intelligent civilizations that might exist in our galaxy. The year was 1961, and the scientific community was beginning to seriously grapple with the question of extraterrestrial life. It was during this pivotal time that astronomer Frank Drake presented a groundbreaking formula that would forever transform our perspective on the search for alien life. Rather than leaving this question to pure speculation, Drake's approach brought mathematical precision and scientific methodology to a field that had previously been dominated by conjecture and imagination. Today, we're going to embark on an incredible journey through this equation that has captured the imagination of scientists, astronomers, and dreamers alike. We'll unravel each component of Drake's revolutionary formula and discover what it tells us about our potential cosmic neighbors. This isn't just about numbers and probabilities. It's about understanding our place in the cosmos and the possibility that somewhere out there, another civilization might be asking the same questions we are. As we delve into this fascinating equation, we'll explore not just the mathematics, but also the profound implications it holds for our understanding of life in the universe and our potential place among the stars. The Drake equation stands as one of humanity's most ambitious intellectual endeavors. Far more than just another mathematical formula written on a chalkboard, it represents our first scientific attempt to accomplish what many would consider impossible: calculating the number of intelligent alien civilizations that might exist in our Milky Way galaxy. This groundbreaking equation transformed what was once purely philosophical speculation into a framework for scientific inquiry. The true genius of Drake's equation lies in its elegant simplicity. While the concept of finding alien life might seem overwhelmingly complex, Drake managed to break down this cosmic question into 7 fundamental factors that, when multiplied together, provide an estimate of how many civilizations might be out there capable of communicating across the stars. This systematic approach turns an almost unfathomable question into something we can actually analyze and discuss in concrete terms. Dr. Jill Tarter, one of the world's foremost authorities on the search for extraterrestrial intelligence, perfectly captured the equation's profound significance when she said, "The equation forces us to quantify our ignorance about life in the cosmos." This statement cuts to the heart of what makes the Drake equation so powerful. It doesn't just give us answers, it helps us understand what we don't know. Each variable in the equation represents a distinct aspect of our cosmic uncertainty, from the rate of star formation to the likelihood that life will evolve into intelligent beings. What makes the equation particularly fascinating is how it serves as a bridge between what we can observe and what we can only speculate about. Some of its variables, like the rate of star formation in our galaxy, can be measured with increasing precision through modern astronomy. Others, like the fraction of planets where life actually develops, remain profound mysteries that push the boundaries of our scientific understanding. By breaking down the search for alien life into these discrete components, the Drake equation provides a roadmap for future scientific research, highlighting exactly where we need to focus our efforts to better understand our place in the cosmic community. As we begin to examine each component of this remarkable formula, We'll see how it not only helps us estimate the number of potential alien civilizations, but also tells us something profound about our own existence. Each variable in the equation represents a crucial step in the journey from basic cosmic materials to intelligent life capable of reaching out across the stars. And understanding these steps gives us insight into our own cosmic story. Let's dive deep into the fascinating first elements of the Drake equation, where we begin to see the incredible scope of possibilities for life in our galaxy. The first factor in Drake's equation starts with something surprisingly concrete: the average rate of star formation in our galaxy. Modern astronomical observations have revealed that our Milky Way creates approximately 7 new stars each year. This might seem like a small number given the vast size of our galaxy, but remember, this process has been ongoing for billions of years. Each of these newborn stars represents a potential cradle for life, emerging from vast clouds of gas and dust in the cosmic dance of creation. When we move to the second factor, we encounter one of the most exciting discoveries in modern astronomy. When Frank Drake first proposed his equation in 1961, we could only speculate about how many stars might host planetary systems. Today, thanks to powerful telescopes and detection methods, we've made a stunning discovery. Nearly 100% of stars appear to have planets orbiting them. This revelation has dramatically increased our estimation of potential habitats for life. Just imagine, virtually every point of light you see in the night sky is likely to be surrounded by its own family of worlds. The third factor brings us even more intriguing data: the average number of potentially habitable planets per star system. Current estimates suggest that approximately 40% of star systems may contain planets in what astronomers call the habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. This percentage is remarkably high, suggesting that our galaxy could be teeming with planets that have the basic conditions necessary for life as we know it. To put these numbers in perspective, consider this. Our Milky Way contains roughly 200 billion stars. If nearly all of them have planets, and 40% of these systems contain potentially habitable worlds, we're looking at tens of billions of planets that could potentially support life. The sheer scale of these numbers is nothing short of extraordinary. These revelations about our cosmic neighborhood have transformed our understanding of the universe. What once seemed like a vast, empty space is now revealed to be an abundance of planetary systems, each with its own potential for harboring life. Every new exoplanet discovery adds to our understanding and continues to surprise us with the diversity and prevalence of worlds beyond our solar system. Isn't it absolutely mind-blowing to consider these discoveries? The universe turns out to be far more rich with possibilities than we ever imagined. If you're as captivated by these cosmic revelations as I am, make sure to hit that like button and subscribe to our channel for more fascinating content about the mysteries of the cosmos. Together, we'll continue to explore these incredible discoveries that are reshaping our understanding of our place in the universe. Now let's explore perhaps the most mysterious and captivating elements of the Drake equation, the biological factors that address the emergence of life and its evolution into intelligent forms. The fourth and fifth factors of the Drake equation venture into territory that pushes the boundaries of our scientific understanding. These factors ask two profound questions. What is the probability that life will emerge on a suitable planet? And if life does appear, what are the chances it will evolve into intelligent beings capable of developing advanced technology? The fourth factor, the likelihood of life emerging, remains one of science's greatest mysteries. While we know that life appeared on Earth relatively early in its history, possibly as soon as 300 million years after our planet's formation, we still don't fully understand how this process occurred. Recent discoveries in prebiotic chemistry have shown how complex organic molecules can form spontaneously under the right conditions. But the leap from chemistry to biology, from non-living matter to living cells, remains a fascinating frontier of scientific research. Dr. Carl Pilcher's observation that each new exoplanet discovery refines our understanding of these numbers is particularly relevant here. As we discover more planets and study their compositions, atmospheres, and environmental conditions, we're building a better picture of the various environments where life might potentially emerge. For instance, the discovery of liquid water beneath the ice of Europa and Enceladus has expanded our understanding of where life might exist, suggesting that even worlds far from their stars' habitable zones might harbor the conditions necessary for life. The fifth factor, the evolution of simple life into intelligent forms, is equally compelling. On Earth, life existed for billions of years before intelligence emerged in the form we know it. This raises fascinating questions. Is intelligence an inevitable outcome of evolution given enough time? Or is it a rare accident, the result of a unique series of circumstances and evolutionary pressures? The fossil record shows that while life itself seems to appear relatively easily, the path to intelligence is far more complex and perhaps less certain. We're also learning that intelligence might take forms very different from what we traditionally imagine. Studies of dolphins, octopi, and even slime molds have revealed fascinating forms of problem-solving abilities that challenge our understanding of what intelligence means. This suggests that if life does evolve elsewhere, intelligent aliens might be far more diverse and different from our expectations than science fiction typically portrays. Modern research in astrobiology is providing new insights into these factors. For instance, the study of extremophiles, organisms that thrive in conditions that would be lethal to most life forms, has shown that life can adapt to an incredibly wide range of environments. This suggests that once life gains a foothold, it demonstrates remarkable resilience and adaptability, potentially increasing the chances of eventual intelligence emerging. The interplay between these two factors, the emergence of life and its evolution to intelligence, represents one of the most profound questions in science. While we can't yet assign definitive numbers to these probabilities, each new discovery in biology, chemistry, and planetary science helps us refine our estimates and better understand the potential paths that might lead from simple chemistry to conscious beings contemplating their place in the universe. These factors remind us that the Drake equation isn't just about astronomy. It's about understanding our own origins and the possible paths that might lead to the emergence of other thinking beings in the cosmos. As we continue to explore these questions, we're not just learning about potential alien life. We're learning about ourselves and our own remarkable journey from stardust to consciousness. Let's delve into the final and perhaps most thought-provoking elements of the Drake equation, the civilization factors that consider technological development and the longevity of advanced societies. The sixth factor in Drake's equation addresses a crucial question. What fraction of intelligent species will develop technology that we could detect from Earth? This isn't just about developing technology. It's specifically about creating technology that could announce their presence across interstellar distances. This might include radio transmissions, powerful optical signals, or even megastructures that could be visible to our telescopes. Consider our own civilization. We've only been capable of sending detectable signals into space for about a century, a mere blink in cosmic terms. This raises fascinating questions about the technological paths other civilizations might take. Would they necessarily develop radio technology as we did? Might they choose different methods of communication we haven't even considered? The seventh and final factor might be the most crucial. How long do technological civilizations typically survive? This factor, often called L in the equation, carries enormous implications. Will advanced civilizations destroy themselves shortly after developing powerful technology? Or will they learn to survive and thrive for millions of years? Our own civilization's trajectory could provide clues. We've developed both the capacity for self-destruction and the potential for becoming a spacefaring species. This survival factor becomes particularly significant when we consider cosmic timescales. If civilizations typically survive for millions of years, there could be many existing simultaneously in our galaxy. However, if they tend to destroy themselves quickly after achieving advanced technology, the number of concurrent civilizations would be much smaller. This factor essentially asks, are we in a cosmic version of the Great Filter, a crucial test that determines whether civilizations typically survive their technological adolescence? What makes these final factors truly mind-bending is their mathematical impact. Even using extremely conservative estimates for all the equation's factors, the final calculation suggests dozens of technological civilizations might exist in our galaxy right now. Let's break down some conservative numbers. If only 1% of intelligent species develop detectable technology, and if these civilizations typically survive for just 1,000 years, given all the previous factors we discussed, star formation, habitable planets, emergence of life, we still end up with a surprising number of potential civilizations out there. If there are indeed dozens of civilizations in our galaxy, why haven't we detected them yet? This paradox, famously articulated by Enrico Fermi, becomes even more puzzling when we consider the Drake equation's results. Are they too far away? Are we looking for the wrong signs? Or are we simply not looking hard enough? The civilization factors of the Drake equation do more than just complete a mathematical formula. They force us to confront existential questions about our own future. As we develop more powerful technology and face global challenges, understanding the typical lifespan of technological civilizations becomes not just an astronomical question, but a guide for our own species' survival and development. These factors remind us that our search for extraterrestrial intelligence isn't just about finding other civilizations. It's about understanding our own place in the cosmic story and perhaps learning crucial lessons about how technological societies can survive and thrive in the long term. Whether or not we're alone in the galaxy, the very process of thinking through these factors helps us better understand the challenges and opportunities that lie ahead for our own civilization. As we reach the conclusion of our journey through the Drake equation, it's important to recognize that its true value lies not in providing definitive answers, but in giving us something far more precious, a framework for contemplating our cosmic existence. This remarkable equation serves as a lens through which we can examine some of the most profound questions humanity has ever asked. While the Drake equation may not tell us exactly how many alien civilizations exist, it accomplishes something perhaps even more significant. It transforms an overwhelming philosophical question into a series of smaller, more manageable scientific inquiries. Each variable in the equation represents a stepping stone in our understanding of life's place in the cosmos, from the birth of stars to the evolution of intelligent life. This systematic approach helps us organize our thoughts about something as vast and complex as life in the universe. The equation's real significance transcends its mathematical nature. It serves as a cosmic mirror, reflecting back at us our own understanding, and more importantly, our own ignorance about our place in the universe. When we work through each factor, we're not just calculating probabilities, we're engaging in a profound meditation on existence itself. We're forced to confront questions about the rarity of life, the uniqueness of intelligence, and the fragility or resilience of technological civilizations like our own. Perhaps one of the most poetic aspects of the Drake equation is how it changes our perspective when we look up at the night sky. Each twinkling star becomes not just a distant sun, but a possibility, a potential cradle for life and intelligence. When we gaze at the countless stars scattered across the dark canvas of space, we can't help but wonder, how many civilizations might be out there, gazing back at their own night skies, asking the same questions we are? Are they also using their own version of the Drake equation to wonder about us? This brings us to a deeper truth about the equation. It's not just a scientific tool, but a philosophical compass that guides us toward better questions about our cosmic significance. Whether the final number is 0 or 1,000,000, the process of thinking through these variables enriches our understanding of our own existence and our potential future among the stars. Before we conclude this cosmic journey, I want to invite all of you who have been captivated by these possibilities to join us in exploring more mysteries of the universe. Subscribe to our channel, Exploring the Universe, for more content that pushes the boundaries of our cosmic understanding. Each video is a new adventure into the unknown, a fresh perspective on the wonders that surround us in this vast cosmos. Thank you for joining me on this exploration of the Drake equation. Remember, every time you look up at the night sky, you're not just seeing stars, you're seeing possibilities. Until our next journey together through the mysteries of the universe, keep wondering, keep questioning, and keep exploring the cosmic ocean that surrounds us. See you in our next video, where we'll continue our quest to understand our place among the stars.